Hi everybody. Welcome to the bi-weekly Trusty Firmware .org TFA Tech Forum meeting. Today we've got a presentation by Alexei and Javier, who will be presenting information about the TFA measured boot implementation and some test capabilities we've been building in. Please mute yourself if you're not asking questions. I suspect Alexei will take questions. Well, I don't know, Alexei. You can say how you want to take questions during your presentation, whether you want it as we go or at the end.
So just a second. My
Not sure what that was. Without much further ado, Alexei, do you want to take over and start your presentation? You're mute at the moment. Hello, Alexei. There you go.
Okay, so I'll present the measured boot implementation for the measured boot driver in TFA today. So please ask any questions if you're interested. So I'll start with the first slide now. Oops. Okay, first of all, what is measured boot? So the measured boot helps to measure firmware components and record them in a platform storage device, such as Trusted Platform Module, or TPM. So the recorded measurement can be compared with the golden value. For example, the expected unique measurement that was calculated on a known good system. And if the measurement doesn't match the golden measurement, the system integrity is considered compromised. So the integrity of a remote system in this case can be ascertained by comparing the measurements reported by the system to the golden value. So the goal of implementing the measured boot driver for TFA was to supply measured boot capability to the existing images during TFA boot flow, and supply secure event log and APIs that support the event log creation and passing event log to a platform provided TPM solution. Then Javier will cover the FTPM test service, and we will provide the guidance for the platform providers to supply a full measured boot solution. So what is the event log in the measured boot driver? The event log is the record of measurements made to PCRs by the platform firmware. PCRs are platform configuration registers, and the information with some informational events which are not extended to the PCRs, and informational events which are extended to PCRs are passed in the event log. So event log is a secure buffer which contains all the measurements for all the images or data structures which were loaded by the TFA bootloader during the boot process. So TFA needs to measure image boot for a variety of undefined platform TPM solutions. Currently, we support only FVP platform because this is the only one platform which is available to us. We don't have any access to the platforms with the hardware TPM. And Javier created a service which writes the measurements provided by the measured boot driver to firmware TPM. So he will cover this issue later. So on the original implementation of the measured boot driver, we had a feedback from the interested parties. So all of them are listed here below. The feedback was about upgrading, changing the hash algorithm. I will talk about a bit later. So then there was a request to provide a new API for passing platform-specific image data, which will be done, which already done, and I'll talk about later as well. And there also was another request from other people, and I think in the future we'll take a look at these requests later. So going to the next slide. So this is the measured boot flow, with different stages, which will be covered on the next slide. And there will be provided more detailed information about the implementation, how it's related to the measured boot and TFA. So measured boot driver uses hash algorithm, which is provided as a TPM hash alg build parameter. And this build parameter is used by embed TLS. So this parameter takes the same values as the hash alg parameter, which is used for the trusted bot boot. So it has three options with different key sizes. So 256, 380, 384, 5112. And the hash size is respectively 32 bytes, 48 bytes, and 64 bytes. So when the platform resets, the boot ROM, and in our example, it's BL1 image, it executes, verifies, and boots the first firmware image, which is BL2. Then it transfers control to BL2 image, and in our case, BL1 calculates BL2 hash and passes these measurements as a parameter to BL2. So this data is passed in the DTB file, which has a new property added with the name BL2 hash data. And this is a byte array, which depends on the algorithm which was provided as a build option. So this byte array contains either 32, 48, or 64 bytes. After control was passed to BL2, so BL2 performs normal initialization and receives its own hash from BL1 image via the DTB file. So there was a discussion how BL2 should calculate its own hash. So there was a possibility to calculate its own hash by BL2 itself. But the problem is that by the time when the measured boot driver starts, some of the global data variables and the memory was initialized. So if you calculate hash by BL2, in this case, the hash stored will calculated will be different to the hash which is stored in the FIP image, and in some cases it's not acceptable. So BL2 initializes measured boot driver and writes all the measurements done for itself. In our case, it's BL2 image because only BL2 was actually downloaded in the TPM event log, which is a buffer in secure memory. After that, BL2 loads all other images. In our case, it's 31, 32, 33, and any critical data which are provided by the platform. And all the measurements are written in the TPM event log. Then partition code, BL2 secure partition code is initialized when the control is passed from BL2 to BL31. Then TPM secure partition service gets initialized. And this initialization process includes TPM initialization, reading the event log, and all the measurements and writing all the measurements from the event log into the TPM. So in the DTB file, there are two properties added for providing information about the existing event log which was written. So they hold the event lock address, which is unsigned 64-bit integer, and 32-bit integer which holds the event log size. So this is a structure which defined in the DTS file to provide information about event log address and size itself. So then when control passes to BL33 or UEFI image, UEFI can measure its own drivers and programs, and which can be loaded from either internal or external storage, and also it writes the data to to the TPM and event log. So in this case, TPM event log should be copied to non-secure memory because UEFI runs at ETL2 non-secure world. So BL2 calculates the memory for the copying event log in non-secure memory by considering these options. So it takes the maximum size of NT firmware config DTB file, gets the start of the NTFV config address, and after that it allocates the memory in non-secure memory for the event log and copies data from secure memory to non-secure memory. So at this stage, event log is provided by the measured boot driver to BL33 in non-secure firmware config device 3. And the address for this NTFW config DTB file is passed from BL31 as a arg0 parameter. At the final stage, bootloader can measure OS kernel and writes its own data to TPM. It can be done via SPM TPM service. And so event log will be expanded with the new data, which will be calculated and measured at this stage. So the measured boot driver in TFA has 3 build options. The first one is the hash algorithm, which I explained earlier. Takes 3 values. Default value is SHA 256 with a hash size equals to 32 bytes. And the second parameter is event log size. So default value is 1 kilobyte. And this is an example of how much of this buffer is actually used. So on FEP platform, which boots TFTF, we have 4 recorded events. And here are the numbers which were got from the event log print messages. So the highest value here is 710 bytes for the hash size equals to 64 bytes. And then recently, in the recent page provided by Javier, there was a new parameter added called event log level. So it chooses the event log level for the printing messages from the measured boot driver. The default value is 40, which is log level info. So now I'll try to cover platform specific details. So we have 2 structures defined here. So platform specific data are provided in the form of the structure measured boot data T, which has the pointer to images data and pointers to 2 functions. One of the function sets the data for the event log in the NTFV DTB file, which is a non-secure DTB, and another is for the trusted OS firmware info DTB file. So the first entry in this structure, the first field is the images data, which has a type of image data T. So it's a pointer to array of these structures. And for each image or the data which are booted by BL2, we've got a image or data ID. Then we've got a name for this image on the top, we've got examples of such names. So it's just the name of the DTB file or the bootloader, which is loaded. And the next parameter is unsigned int type, which is a PCR. So the PCR is a platform configuration register. And it shows for each individual image or data loaded, it shows the number of PCR register which should be written with the data provided by the entry in the event log for this data or for the loaded image. So by default, we have these entries. So for the flat images data, we've got the first entry, which is actually BL2 image itself. And the first entry is reserved for BL2. And the last entry should be a terminator with invalid ID. String will be null because we don't have a name for the terminator. And PCR value should be invalid value, and it will be -1 in our case. Then the platform-specific data, it has the pointer to this entry, so which will contain just 2 records, so BL2 and the terminator itself, and null pointers for the functions which should write the data to NTFW and TOSFW. So if these pointers are null, no data will be written to these DTB files. And the function which provides the address for this platform-specific data is called the platGetMeasuredBootData, which has void parameter but returns the pointer, const pointer to the platform-specific data. Now I'll show the example of FVP. So this is the images data entries in the platform-specific images data array, which has all the images and all the DTBs which can be loaded by BL2 loader. So you can see the BL2 string is the first one, and the last one is the terminator itself. And the platform-specific data contains the pointer to this array of structures and the pointers or the start addresses of 2 functions which are provided for FVP itself. So for FVP platform, we just return the address for this platform-specific measured boot data. So we had some feedback when the first series of patches were provided. So the first one was about making the hash algorithm runtime available. So the problem here is that when you compile statically embed TLS, you provide the hash algorithm, and based on this hash algorithm, embed TLS allocates its own buffers. So in the case when we support the runtime setting of the hash algorithm for measured boot, we will have to get the maximum size of all the internal embed TLS buffers. In some cases, it can be impractical because we don't know which hash algorithm will be used. So by default, we need to allocate the maximum buffers. And for example, for FVP, when we have the restricted and limited size of secure memory, sometimes it won't be able to build the measured boot driver with some other options enabled, for example, BTI or PAuth, because BTI ends 1 extra instruction in each function. And this TFA contains about 1,000 functions already. So you can get the increment of secure memory, which is not available on FVP platform. But it's still under discussion, and I think we can return to this implementation a bit later when we have requests from our partners. But in this case, we will have to implement a new API which will pass any hash algorithm during the runtime. And measured boot driver should be modified to allocate its own buffers, which will enable usage of the maximum hash algorithm size of 64 bytes. Then there was a request to provide supported platform-specific images, IDs, and image data, and PCR, which should hold the number, which should be written for individual image or data structure. And this was implemented in the latest patches, and they already merged in the TFA master branch. Then there was a request to provide additional flag in the NTFV FW config DTB, which will show that the TPM was actually written. This is planned for a future work when we have the complete integration of the current implementation of measured boot driver and firmware TPM service. Yeah, I think it's all from my side, and I can show you how the event log debug messages look like when you run the TFA image. So I need to close this slide, and I will. So can you see my screen with a new window open? Hello?
No, we still
Yes,
see
we can see it.
So you can't see it, or you can. So you are at log, you are at 0 log. Can you see this?
All I'm seeing, Alexei, is your feedback for future work slide, not in presentation mode.
Okay, I think I need to stop share and then open a new window with the share. Is it okay if I stop share?
Yeah, go for it.
Okay, now. Share screen. Yep.
Yeah, we can see a UART 0 log.
Yes, so this is the normal log, but with measured boot driver support when we boot TFTF. So we can see that I just added this debug message to show the size of the event log. So it won't be, it's not present in on the master branch, so it was just for debugging and providing information for my slide. So you see all the events which are written in the event log. So the first event, according to the TCG, which is a trusted computer group specification, is event of this type, which actually says what kind of the hash algorithm will be used. And the second event written is the event log of startup locality. So this was compiled for SHA 384 with 48 bytes of the hash algorithm. Size of algorithm is 48 bytes. So you can see that all other events, which are BL2, BL31 hardware config and all other configurations, are present here. And then we boot TFTF and run all the tests. So this output is controlled by the one of the build parameters, which is event log level. So if you don't want to see this, you can set the log level to the small amount, and you won't see this output. So you see that we were able to run the TFTF with this measured boot driver enabled, and nothing has crashed so far. But I had to stop the execution because I was only interested in the event log size to put this data in my slide. That's basically all from me. So please ask your questions if you have any. Okay, I think there are no questions. And Jana, shall I stop my screen sharing?
Yeah, if you stop, and then Javier can share his and show his work.
Okay. Yeah, thank you for listening.
You there, Javier?
Yeah, I'm on it. Give me a second. So, can you guys see my screen?
Yes.
Okay, cool. Thank you very much, Alexei and Joanna. Hello, everyone. My name is, for those who don't know me, my name is Javier. I've been working on ARM for the past few months. I think it has been almost a year now. Part of my work during this time has been helping Alexei on his work with TPM, measured boot driver, and for that, well, what I was covering was the need that we had to test a measured boot with a real TPM service. So, as Alexei pointed out before, measured boot needs to be supported by TPM, which is used to securely extend and hold all the images measurements that are stored on the event log. So this TPM needs to meet some criteria. So, for instance, the TPM must comply with the TPM 2.0 specification, which is a specification written by the Trusted Computing Group. And this TPM can be provided either as a silicon or as a secure software service. So the measured boot driver should be agnostic about the type of TPM device that we are using. So because of that, we need some sort of mechanism to test and validate that our current implementation of measured boot was able to interact with a TPM 2.0 compliant device or service. So that first raised the first question, which was, what are we testing? What do we want to test, and what don't we want to test? So we need to test that the measured boot driver is able to generate a TPM 2.0 compliant event log. So TFA must be able to pass the event log to the TPM service in a secure manner. The TPM service should be able to parse the event log and extract all the relevant information from it, such as the digest and for which PCR this digest is. And all the events present on the event log must be successfully extended by the TPM. That means that the information on the event log must make sense. It has to be well formed. And also, what we don't want to test. So we are not validating the TPM records. So we are not providing a TPM service. We are just testing the compatibility between our measured boot driver and a TPM service. So we don't test if the record have been properly extended by the TPM service. This is beyond our scope. This should be tested by the TPM provider. So therefore, we don't make any kind of assumptions about the correctness of a particular TPM or a TPM service. So all we want to check is that a TPM can understand what a measured boot is giving to it. So after we decided what to test on and what we didn't want to test, we have to make some design decisions. So we started thinking about how do we want to implement this TPM or pseudo TPM service. So we consider different approaches. So first thing we considered was to implement this service as an SPCA secure partition. We also considered in case that the trusted firmware didn't have support for SPCA secure partition, because we started thinking about that, I think, at the end of 2019. So in case TFA didn't have support for SPCI secure partition, we also consider the option of writing an secure partition running on BL32 as well. And we also check if there was some other TPM or firmware TPM service out there running mostly on Opti, as we know that this is a widely used service. We know that Opti is adopted by many of our partners. So we decided to go with that latest option, as we found a TPM reference implementation written by Microsoft, which is TPM 2.0 compliant. And that implementation also includes support for generic ARM32 architecture. So that will save us out of time, and also could be used by many of our partners for the products. That implementation ran on Opti, and we know that Opti is widely used by many partners. So then we decided to go ahead with that approach. So what is this TPM service that we decide to use then? So this is an official Trusted Computing Group reference implementation of the TPM 2.0 specification. It is available on GitHub from the Microsoft account. It is available with an open source license, but I cannot recall exactly which one. And the implementation consists mainly of a library which implements the TPM 2.0 specification, and it comes with some applications built around that library. So it comes with a simulator application that can be built for the same host machine in which you are compiling the library. And you can exercise some of the TPM functionality and see how it works. And it also comes with some sample applications for different boards and architectures. At the time of writing this document, there were mainly two different sample applications. One was based on ST Nucleo boards, and the other one was based on ARM32 generic architecture. So we decided to focus on this latest one, as that could be something that we could use on our CI system. So yeah, we started working on that, and then shortly after that, we noticed that we had a few requirements to fulfill. The first requirement was related to Opti. So as Alexei pointed out before, during system boot, BL2 needs to keep an lock in secure memory, as the TPM service will not be available yet. So then once the TPM service is ready to boot up, Opti need to pass to that TPM service the address of the event lock in secure memory, as well as the size of the event lock. The problem that we have here is that there were no way for Opti to pass parameters to a trusted application when the trusted application is boot up for the first time. So we decided then to add a new system call to Opti, through which a trusted application, the TPM service in this case, could request to Opti a copy of the event log, right? This was added to Opti, was merged into their main line. So this new system call is now available if you download the latest version of Opti. So pretty much the way in which this works is explained in this slide. So basically, during the initialization, Opti parses the device free blob that is passed to it. And on this device free blob, we have, as mentioned before, the address of the event log and its size. So when Opti boots up, it just reads that and maps the event log, the copy of the event log in secure memory internally, and makes a copy of the size internally. So then once Opti has that information, what it does is to set those parameters in the DTB to 0. The reason for that is because Opti at the moment doesn't have support to receive a DTB held in secure memory. So we have to pass a DTB which is held in unsecure memory. And in that DTB, we have an address that belongs to the secure world, which is where the event log is. So in order to avoid any leakage of information, as soon as Opti has the address and the size of the event log, it sets those parameters to 0 to avoid any further problem. So now that Opti has that data and has the event log in secure memory mapped inside. So what happens when we have a TPM service putting up is that this TPM service requests a copy of the event log that Opti has, and then Opti what does is just send that copy to the trusted application, in this case the TPM service, and then the TPM service just extends the records and store the measurements into the PCR that corresponds. So that was the first requirement to fulfill from Opti side. But we also have some other requirements to fulfill on the FTPM service itself. So, as I said before, we were using Microsoft TPM implementation.
Hey, sorry to interrupt. Right, I had a quick question.
Yeah.
So the integrity of the event log is maintained until the TPM service passes it. So is it always in like secure RAM or something like that?
It is always in secure RAM. Opti. So TFA has two copies of the event log. One is in secure memory, the other one is in non-secure memory. So Opti only receives the copy that it is in secure memory. And Opti passes that copy to the TPM, which is also running in secure memory, in the secure world.
All right. Yeah, I have some feedback on this and a couple of questions, but I'll wait for you to finish the presentation. Thanks.
Okay, cool. Thank you. So yeah, as I was explaining, Microsoft had an implementation of the TPM library, and then there were a couple of ports or applications for different architectures based on that port. The problem is that the application for the ARC32 architecture seems to be outdated. I don't know if it was abandoned or not, but seems to be outdated. So it wouldn't be built out of the box. So one of the first things we had to do was to catch up the ARC32 application, Opti application, with master branch, so we would be able to build the original application. So we did that, and now the application is able to build and run out of the box. The second requirement that we had was obviously to add support on this FTPM service to be able to receive a TPM, an event log using the system code that we added to Opti, and then extend the records upon boot up. So now when this FTPM application starts, first thing that it does is to ask for a copy of the event log to Opti, and then extends all the records available on that event log. So something that I like to point out here is that those patches are at the moment internal to ARM. We are undergoing internal review for those patches, and as soon as those patches are reviewed, we are going to raise a pull request to Microsoft repository, so then they can review those patches and integrate those patches with their mainline. So any any partner or anyone interested could download those patches and use this FTPM service. So once we have the requirements fulfilled, we have to think about the test pass criteria for our continuous integration system. So what we wanted to test here is, as I explained before, that we can interact with that event log, but we don't want to test that the records held by the TPM service are correct or not, because that's beyond our scope. So then we came with the following list of things that we wanted to check. So we wanted to check that the TPM service can receive the event log as it is generated by TFA. That means that the TPM service must receive exactly the same copy of the event log that TFA generated. So for this, what our automated test system does is TFA prints a copy of the event log, as Alexei showed before, and so does the FTPM service. In fact, it uses exactly the same functions. We copy the functions that Alexei wrote to dump the event log into the FTPM. So both TFA and FTPM must print exactly the same event log. So then the CI system just holds a copy of the TFA event log and holds a copy of the FTPM and compare both of them. If they are different, the test fails. If they are the same, means that the FTPM service was able to get an exact copy of the event log generated by TFA. We want to also check that the event log is successfully processed by the FTPM service. That means that no errors are generated by the FTPM service when it is initialized. So the first thing that the FTPM service does now, when boot up, is to request for the FTPM service and extend the records. If there were any problem on the event log, the FTPM service should throw an error, and then we should be able to see that error on the event logs. We also must check that PCR 0, which is where the event log is extended, is not all zeros. So if it were all zeros, means that we didn't manage to extend any of the digest on the event log. Also, we want to check that the event log is well formed, meaning that information there makes sense, that the TPM service is able to read and interpret that data. So for that, we also check that PCR 0 is not all zeros, as we did for the case before. And we also expect that any PCR other than 0 is all zeros, because TFA doesn't extend anything, it doesn't log anything for a PCR other than 0, at least for now. So that was our overall test pass criteria. So once we implemented all those tests in our CI system and run them, we could see the results, as we can see in this couple of screenshots. So what we have first, on the first one, is that build root runs. This is an FVP model. We get a PCR 0. We can see that this is not all zeros. The rest of PCRs are 0. And then finally, we spawn a diff process that compares the TFA event log with the event log generated by the FTPM, which are held in different files. And if those files are the same, then we can confirm that FTPM received exactly the same copy of the event log as generated by TFA. And then once all those conditions matches, we mark the test as succeed. So those scripts are actually on our CI system. They were integrated early this week. And we are testing those tests now with the rest of patches and to work. So yeah, that was, yeah.
Sorry, a question on this, right? So So this is running from Linux, right? So are you using the stock kernel driver, and are you using the CRB driver, or is it some other driver of your own?
Yeah. So we are using. I was going to go on this in the next slide. So we are using actually.
Oh, sorry. Okay.
No problem. In fact, I'm going to explain the next slide, and then I will answer your question as I explain the next slide. Is that okay? So yeah. So now, what is the pending work that we have that we still have to do? So at the moment, as I explained before, all the contributions that we've made to FTPM they haven't been merged to Microsoft repository. We are undergoing internal review of those patches. So as soon as they are ready, we will try to merge them with Microsoft repo. Also, the build system that we use to build all those images. So all those images work for FVP, and the build system is based on the Opti toolkit. So we are working on pushing all those changes as well to Opti repository, so they would also be available to all the partners. So that also is related to the question that I had before. So what we use actually is the same. We use a mainstream kernel. We use a mainstream build root. We use an IBM TSS application. It was called TSS application, I guess, written by IBM as well. We use a driver for Opti on the kernel, and then we use the FTPM. We also use UEFI to boot up everything. And then we used Opti, which is also mainstream, and this FTPM application. So once we have everything merged on Microsoft side and on Opti side, what we want to do is to write to update TFA documentation, explaining how all these images can be built by hand, and then how can you run all those tests by hand on your host. So at the moment we are working with pre-built images that I built on my workstation. But as soon as we are able to match everything, we expect that partners will be able to download all the source code and build everything automatically. That should be very easy to do because we integrated this with the Opti toolkit. So if any one of you has ever used the Opti toolkit, you know that when you build the Opti toolkit, it generates a build root image with a Linux image, and then also builds a Opti and builds everything together, and then it can run. It can bring up an FVP model, loading everything, and then you should be able there to test your application. So this is pretty much the same. The only one difference is that the TFA we use there, it has a measure boot enabled, and it automatically builds and installs on that image the FTPM service. So then you can just use the FTPM service from the FVP console. I don't know if that answers your question.
No, not really. So I'm asking. So there's a TPM kernel driver, right? And your IBM TSS stack uses a stock Linux kernel driver. So does it need? Did the kernel TPM driver need modification to
no.
Interact with the Opti driver?
No, it doesn't need any modification.
Then how? I guess I'm wondering how does it get routed to the Opti TA correctly?
Sorry?
Let's say I've got a PCR read or whatever.
Sorry.
So if you've got a PCR read command, for example, right? I'm just wondering what the call path is.
Yeah, this is a library written. Well, it's actually an application written by IBM, but I cannot remember the name actually. It's called IBM TSS, I guess. So that's pretty much an application that just interacts with the TPM service. So the TPM service is loaded, right? And Opti loads the service, and then the service is available, and then we load a kernel driver for the TPM service, and then this application IBM TSS. I can write an email on the list later about that, explaining this a bit more in detail. So then what happens is that this IBM TSS library or application, what it does is just interacts with the FTPM driver, and the FTPM driver actually interacts in turn with the FTPM service, because the FTPM service is meant to use a standard interface. So then the driver should be able to interact with the TPM drive, with the TPM device.
Right. So that's not the stock. That's not the stock kernel TPM driver. That is an FTPM driver. That is, that is specific to Opti, right? That needs to be loaded.
Yeah, but if I'm not wrong, that kernel driver is also included on the kernel.
Yeah, I don't believe so. It's possible it's changed. It's been a while.
Yeah,
since I looked, but
I will double check, because as I mentioned before, I started working on this like in December, so I may have missed a part. I may have missed that part. So I'm going to double check, and then I will send an email on the list once I can confirm this part. Is that okay?
So, if I may add, an FTPM driver was floated for Linux. I think it has been merged in Linux. I'm not sure of the current status, but last year in 2019, an FTPM driver was, patches for the FTPM driver were floated for Linux.
The FTPM driver is supposed to work on an Opti.
Yes, it interacts with the TE driver.
An Opti service, okay.
Right. It interacts with the TE driver to talk to the FTPM. So I had one question. So you're talking about the FTPM over here, but what about the platforms if they have a hardware TPM implementation? In that case, who would be, because till the BL31 stage measurements are being made. So who would be responsible for writing to the TPM driver? A TPM driver, I guess the first TPM driver would come in the UEFI or U-boot. So are you kind of thinking of a flow where U-boot or UEFI goes and kind of populates these measurements in the TPM for the hardware TPM case?
Sorry, I don't know if I got your question. So you are asking in the case of a discrete TPM.
Right.
So in that case, how is U-boot or the kernel send its measurements, right?
Right. First of all, how would so the measurements which are being done by TFA currently they are being passed to Opti and then to the FTPM service. So how would the flow look like? So where these measurements would be passed?
In that case, I think it should be platform dependent, right? So, for instance, the bootloader may pass the event log to the TPM. It will depend on how the TPM is implemented, or it will be. I think it will be platform independent actually. Platform dependent in that case.
Okay.
So I actually had a question along similar lines, right? So does that mean BL1 passes the measurement to BL2 and then it's written to the DTB, right? Is there no platform hook where I can write those measurements to a physical TPM? Is that a platform hook, or I don't remember?
MeasureBoot works in the case in which we don't have a physical TPM device, or in the case in which the TPM device cannot be working until a later stage. So, for instance, if you have a physical TPM device, which is available from the moment in which the system is powered up, then you don't need MeasureBoot. Then your your bootloaders will just send the measurements to the TPM and it will extend them. In other cases, for instance, in which I know that there are cases in which you have a TPM which depend on Opti. You have an Opti application that runs that discrete TPM. In that case, you cannot extend your records until Opti is up and running. So in that case, you need measure boot. Once Opti is up and running and your application in Opti is up and running, you pass the measure boot there, and then it's platform dependent how you pass that data to your discrete TPM. Don't know if that answers your question.
Yeah, it does.
Okay.
But yeah, I guess. Yeah. So yeah, I think I brought this up even on the email, but it's okay. Sorry, go ahead. Somebody else wanted to say something.
Yeah, I had one more question. Just curious why event log has to be in the secure memory. Since if I understand correctly, that same event log would be appended by the further bootloader stages like UEFI or U-boot, which is in non-secure memory, right? So
Yeah, I was going to go on that actually on the next slide. So the reason why measure boot has to be on secure memory is because during a period of time between the time in which the event log is generated and the time in which we can access to that event log and extend the records inside the TPM, we are exposed and we can suffer a top-toe attack, right? So in order to minimize that, we must hold the event log that is going to be extended by the TPM in secure memory to minimize those chances of attack. We also have a copy of the event log in non-secure memory because if you boot or the kernel boots before the TPM is ready. In this case, for instance, TPM needs this FTPM needs the kernel to be up and running before it's ready. So in that case, we need to extend any measurements made by U-boot or by the kernel. We need to record that on the event log, but the event those processes running on non-secure on the non-secure world shouldn't be able to tamper or to send information or to alter the record that is on secure memory. So then we have another copy on non-secure memory. The problem that we have here is that, as I explained before, the FTPM service can only receive the event log that is inside secure memory. That means that anything that has been added to the event log after via33 boot up, anything that was added to the event log by U-boot or UEFI or the kernel will not be available in that event log, and therefore won't be extended. So we need to think of a way to overcome this problem. This is actually a very specific problem in this very specific FTPM implementation. But yeah, we need to think about a way to overcome that problem.
right. I mean, yeah. I mean, yeah. My intention, what I think is, event log was never intended to be a protected entity, anyways, right? It's the TPM measurements which can be used for the attestation and cross verifying it.
Yeah, that's right. The problem is that if during the time, so we have the event log, and during the period of time between we have the event log and we extend those measurements in the event log, we are susceptible to suffer a top-toe attack. So then this event log has to be protected in secure memory. Once we have those records and we extend those records on the TPM, we use those for attestation.
So like one thing bothering me, like there are scenarios where only Linux is rebooted or U-boot is rebooted, like we have opti and TFA intact as a sequence. Some errors exist, error comes, say FIQ, and we want to reset. So I think that is the situation where we need to copy the PCRs or the event logs stored in SRAM to like we don't need to redo those things. I think that might be that is also a valid reason for that to have there.
Yeah, okay, so yeah, we only reboot the kernel. Yeah, in the case we only reboot the kernel and we don't reboot Opti will keep on having a copy of all what we've done before, and that copy wouldn't be altered because TFA is not rebooting, so we are not redoing stuff. So what will happen then is that, in this case, the kernel, for instance, it will remeasure the RAMFS image or whatever it needs to measure, and then it will add that to the external event log.
Right. Yeah.
Okay. Thanks.
Okay. So yeah, that was actually the end of my presentation. That was everything that I wanted to talk about. Unless anyone has any further question. No? Okay, then.
Well, I do. So, hey, Joanna, can we please put this on next meeting's agenda? Yeah, I think I have some. I'd like to think about this, and I have some feedback. So,
okay,
maybe,
yeah.
Yes.
Yeah, no, yeah. We are going to update this into the Linaro website, I guess, right, Joanna?
Yeah, so yeah, this recording, we're overrunning now the meeting, unfortunately, but it will be made available on the trustedfirmware.org site. Yes, we could talk about this again at the next meeting, but we've also got the mailing list, and I would urge people to reach out on their concerns. Just want to make sure people are aware what we are trying to deliver here. It's primarily the event log and the APIs to manipulate it in the secure world as part of the boot process. We're not trying to provide an end-to-end measured boot implementation here. We're trying to provide those bits that allow platform providers to build that on their platforms. The whole Opti related test service is a test service. It's not our reference implementation for people having an FTPM or a TPM. It's all about being able to test that event log data structure and the APIs that manipulate it in a real example of a compliant FTPM that Microsoft has provided that we're making use of. So the primary delivery of what we're doing here is those APIs and the data structures that we manipulate, and we fill in with event information that has to be recorded before the TPM is actually available. And the point of those APIs is to enable the platform providers on their platforms to access that and migrate that to whatever TPM that they plan to use. I don't know if people got confused about that we're trying to provide a full end-to-end solution in TFA, but we can't do that. That's we've only got the limit of what we can do in the the part of the boot process that that TFA manipulates. But as I said, we can talk about this again next week, or sorry, in a couple of weeks, or I would urge, please raise questions on the mailing list. So we've lost a lot of people, I guess, because we're overshooting. Normally I would do at this point a mailing list discussions if anybody had any, but unfortunately we've run out of time this week. Thank you for everybody attending. I think we've had a record. I think there was 31 people, and I think prior to that we never quite reached that number. So it's good to see people joining and entering into dialogue with us on here. Please follow up on the mailing list. That's where we can continue before the next meeting. Without further ado, I'm going to stop the recording and I'm going to finish the call. Thank you, everybody, for your time. Thank you, Alexei. Thank you, Javier, for presenting.
Thank you, Jonah.
Thank you.